Hi everyone, welcome back to IB Math, and we are continuing our chapter 23, and today we're going to look at something called the binomial distribution. This actually ties in to a topic we did last year, so we're going to bring back an old friend of ours from last year as we get into this a little bit here. So let's talk about an experiment. We're going to call this a binomial experiment, and we talked about expectations last time, and we talked about, there was that one example of if I have a 3 out of 4 chance of kicking a scoring a goal, a footballer scoring a goal, right? So then it was out of 12 chances, you would expect them to get 9 out of 12 because of the expectation, and that was really a probability of success versus failure, right? Success, they make a goal; failure, they don't. And that's kind of what we have with a binomial experiment. There's really just 2 results, either a success or a failure. So we're not going to talk about multiple different outcomes other than a success and failure. So in this example that we have right here, we have a spinner, and you can kind of see the spinner as is one of those that you spin it around, it lands on a side. It looks like there's 3 sides that are blue and 1 side that is white. So we're going to call blue, or landing on blue, we're going to call that a success, and we're going to call landing on white a failure here, right? And of course, if it's an evenly balanced spinner, you know that the chance of hitting blue is going to be 3 out of 4, and the chance of hitting white is 1 out of 4, right? And that's our general general probabilities for that. So let's say I'm going to be twirling the spinner 3 times, and we want the number of successes, right? That is going to be our random variable x, right? So x could be either 0, 1, 2, or 3, right? Based on how many blues am I going to get. So I want to know, what are the probabilities of each of these successes? And we've done that before. And here's a perfect diagram of that, a tree diagram, right? And we could say, you know, for every spin, there's a 3/4 chance of landing on blue and a 1/4 chance of landing on white. And so we look at all the different outcomes, and we spin it 3 times, right? We have our first spin, our second spin, and our third spin. And this is our tree diagram, and we know we're going to multiply those probabilities together to get each end probability, each end result that goes in each one of these spots right here, right? And we've done that before. So if you notice, they do that over to the side here. They say, what is the probability of x equals, was the probability of when x equals 0, that meaning I get none that are blue? Well, that's going to be 1/4 to the 3rd power, right? That's going to be this one down here. It's going to be it's going to be, whoops, let me highlight this. It's going to be 1/4 times 1/4 times 1/4. I get 3 whites, right? So that'd be 3 failures. The other probabilities I could have would be if what would be the probability of me getting of x equal 1, meaning 1 blue and 2 white. And that's what's marked here on their diagram. They have those 3 little green check marks. Those are my 3, whether I get blue, white, white, or white, blue, white, or white, white, blue. There's a possibility of 2 blues and 1 white, and that would be these here, right? That's blue, blue, white, or blue, white, blue, or white, blue, blue, right? And those are the 3 possibilities of that. And then, of course, there's only 1 probability of me getting 3 blues, and that's at the top there, where I would have this one right here, where I've got 3/4 times 3/4 times 3/4. And you can see the math they do each time, right? So they multiply the probabilities together, and then these 2 here, they multiply times 3, right? Because there's 3 of those outcomes. So they multiply the probabilities times 3, and that's going to be my probabilities. And if I add them all up, it's going to look like, here's the one of the little spike diagrams. We've done that before, right? So if I multiply all the probabilities out, and that's what we're doing right here with this case. I get 1/4 to the 3rd power, which is 0.0156, and then I get 3 times 1/4 squared times 3/4 to the first, right? Because that's 1/4 times 1/4 times 3/4. And then I get this number right here. And then likewise for x equals 2 and for x equals 3, those happen to be the same, actually. It works out that way. And those are my probabilities. We know, and what do we know? If I add those all up, those are going to equal 1, right? If I add all those probabilities, that's going to equal 1. Something you might notice about that, though, if you'll notice that the pattern here, the coefficient, which they didn't write here, but that's really 1, and that's really 1. And we have a 1, a 3, and a 1. And that coefficient actually comes from, 3 if I don't choose any, right? 3 choose 0. That's just going to be 1. 3 choose 1. There's 3 different ways I could choose 1. Then 3 choose 2. There's 3 different ways I could choose 2. And then 3 choose 3. There's only one way I could choose 3. So that's just another way of writing it. But notice the x on the bottom as that changed. This is a 0, and that's going to be 0 and 3. And then when this is a 1, that's a 1 and a 2. And it's a 2, it's a 2 and a 1, a 3 and a 3 and a 0. You start to see that pattern here. And what they're saying is that you could really write that for any value of the random variable x. You could really write that as 3 choose x times 3/4 to the x times 1/4 to the 3 minus x. And maybe that looks familiar. And how about this? How about if we just write it out a different way? And we write it out like this here. We're saying if we take each probability, let's do that in a different color. Let's do this in orange. So let's say I've got, if the probability of x equals 0, x equals 1, x equals 2, and x equals 3, the 4 different calculations would be 1/4 to the third, 3, 1/4 squared, 3 times 3/4, times 3, 1/4, 3/4 squared, plus 3/4 to the third. And does that look familiar? Well, actually, that should look familiar because it comes from our old friend, Mr. Pascal's triangle. Remember that? So what this actually ends up being is, if I take all of these, I can write that as a short form. I can write it like this: 1/4 plus 3/4 to the third power. Because if I expand that and multiply that out, that's going to equal this expression, this series of numbers right here. And we know that because of Pascal's triangle, right? So where that n is equal to 3, my exponent's 3, what do I have right here? It's this guy. I underlined it in red. My coefficients are going to be 1, 3, 3, 1, right? And it's going to be a to the third, b to the 0, a squared, b to the first, a to the first, b squared, a to the 0, b to the third. Isn't that exactly what I have up here? So rather than doing a tree diagram for everything, there's actually an algebraic way of calculating the values using Pascal's triangle if I have this type of binomial experiment where I either have success or failures. So I can do that instead of having to do a tree diagram and calculate everything manually every single time. Let me show you an example here. So I have the example and I have the answer written out because I just want to analyze this for you. So we have this expansion of 9/10 plus 1/10 to the fifth. This is what I want to expand. So if I expand that using Pascal's triangle, what do? Well, let's go back up here to Pascal's triangle. This is my a to the fifth, or a plus b to the fifth power. And remember, my coefficients are going to be 1, 5, 10, 10, 5, and 1, right? And my individual terms, a and b, it's a to the fifth, b to the 0, all the way down to a to the 0, b to the fifth. So if I expand it, don't I get this right here? The expansion of 9/10 plus 1/10 to the fifth is equal to this big expansion here. Now, you might be saying, wait, why would I expand that? I already know. Isn't it true that 9/10 plus 1/10 to the fifth equals 1? Well, yeah, we know all the probabilities added together equals 1. But I want to get the individual probabilities for each different value of my random variable x. So if I expand it, I've got that answer that I have in part A. Now look at part B. It says an archer has a 90% chance of hitting a target with each arrow. If they fire 5 arrows, determine the chance of hitting a target either twice only, that's not my highlighter, that's twice only or at most 3 times. So what are the probabilities of me hitting the target twice, right? What's my expected success of hitting it exactly twice? What's the probability going to be? Well, let's see. So I've got a 90% chance of hitting it. That's my 9/10ths of success and 1/10th chance of failure. And then that 5 is going to be the 5 arrows that I'm shooting. Just like I did up here where we said we had 3 spins, right? We use that exponent right up here is 3 because I did 3 spins of the spinner. So I'm going to say that this 9/10ths plus 1/10ths to the 5th means if I have 5 occurrences of this case shooting an arrow, I have a 90% chance of hitting a target. I could draw a big tree diagram with 5 different levels, but I don't need to. I'm going to do this algebraically because now that I've expanded it, what do I know that each one of those terms represents? I know that the 9/10ths to the 5th, that's my probability that I'm going to hit it 5 times in a row. Notice 5, 10, 10, 5, and 1 from my 1 from Pascal's triangle. It's not there. I'm going to draw it in. Now, each one of these represents a different value for x, for my random variable, the number of success results. This is now going to be 4 hits and 1 miss. This is the probability of me getting 3 hits and 2 misses. 2 hits, 3 misses. 1 hit, 4 misses. And what's the probability of me getting 5 misses? Pretty low, right? 1/10th to the 5th power. So now to answer my question, what's the probability of me getting 2 hits only? Well, I'm going to look at this term right here. And it's going to be 10 times 9/10 squared times 1/10 to the 3rd. And that happens to be 0.0081. That's the probability of me getting exactly 2 hits. What's the probability of me getting at most 3 hits? Right? At most 3. So that means I can't get 4 or 5. That means I'm going to look at all of these probabilities right here, right? And again, you would do this on a tree diagram, but who wants to draw a 5-level deep tree diagram, right? I know I'm going to hit, what's the probability of me getting 3, 2, 1, or 0? Well, I'm going to add up all those individual terms for 0, 1, 2, and 3. And I add up all of those, and I can put them all in my calculator or just calculate each one individually, and I'm going to get my probability of 0.0815. Now it seems low, right? But realize, where's most of my probability? I'm a 90% accurate archer here. Most of my probability is that I'm going to get 4 or 5. So I could add those up, and those are going to be the rest of them. But the chance of me getting no more than 3 or only getting 2 are obviously pretty low. And that's how we can use our Pascal's triangle, the binomial expansion, in order to get the same results as a tree diagram, but without having to do all those levels of the tree diagram. We just put, this is my success, right? If I could spell success, and this is my failure, and I put those 2 probabilities in, and I know they both equal, added together, they equal 1, but what is each individual probability? Again, this is in a binomial experiment where I either have a success or a failure, and I'm doing this 5 times, I can have my different outcomes. And that's it. So I want you to try these. Check out numbers 1, 2, 3, and 5. Same idea. You're going to need to do some binomial expansions, and based on these probabilities. So use the format that we just talked about. Remember, it's success plus the failure, the 2 probabilities, raised to the power of how many different experiments or how many different iterations or spins or shots, whatever it is I'm taking, flips, as we go through, and then use Pascal's triangle to expand. And again, here's Pascal's triangle, at least down to the 5th, right? We could keep expanding that. If you recall, where am I getting these numbers from? I'm adding the 2 numbers above to get that. You know, how did I get the 6? That was the 3 and the 3. How did I get this 10? That was the 4 and the 6, right? Added together. It's how I get all my coefficients, right? and use those to get our probabilities. And so here's the assignment for, again, section 23D1. It's numbers 1, 2, 3, and 5. And check those out. And we have an assignment on eCampus as well. Again, if you have any questions, please don't hesitate to email me or ask on the discussion boards, and we'll go from there. Thank you very much for listening. I hope things are going well, and we will talk to you soon.